Now, SCF calculation. SCF stands for self-consistent field. Okay, so this is the procedure you use to determine the best possible expressions for your orbitals, for your spin orbitals. Now, the Hartree method, this was first developed by Hartree. Okay, in Hartree's method, when he did this, he ignored the existence of spin. But let's just go through that because that's easier to understand. Okay, and it will give you an idea of the idea behind this self-consistent field method. The idea here is that you want to get the best possible set of orbital functions to describe the electrons, right? So what you do is you make a guess to start with. So you assume a set of orbitals to describe electrons 1 through n. Okay, so you have electron 1 would be described by spin orbital 1, electron 2 would be described by another function, and so on. So let's call this phi 1, those orbitals phi 1, phi 2, phi 3, all the way to phi n. Okay? If you know the orbital that describes the electron, then you know how that electron is distributed, right? The probability density, that's the kind of information you can get from an orbital, how the electron density is distributed around the nucleus. So what you do then is imagine all the electrons except for one you're interested in, all the electrons, imagine they're just smeared out in your atom. So ignore, in other words, what you can do is you can calculate what's called an effective potential. So you just pretend they don't exist, but they're there, but their presence is felt by, but their presence will still be felt by that one electron you're interested in. In other words, pretend you have a hydrogen atom, you have one hydrogenic system, it's going to feel an effective potential due to the presence of the other electrons. And the potential, okay, the force that the other electrons would exert on that one electron you're interested in would be dependent on what you assume to be the orbitals for those electrons. Okay? So if you assume all of these, then you can solve for a better phi 1 by solving this one electron Schrodinger equation. So in other words, remember your Hamiltonian is, what was it? Negative, it's T1 plus B1, right? Plus T2 plus B2 plus, and so on, plus, and then you have your Bij, your sum of your electron repulsion term, which you're ignoring, right? So what you're doing here is this. You're assuming that the potential energy, okay, of each electron, of one particular electron, would just be the potential energy of interaction between that electron and the nucleus plus an average term resulting from its interaction with all the other electrons. So you reduce your problem into a one electron problem. And when you solve that, here it is. So here's the kinetic energy of electron 1, and you have an effective potential energy. Okay, this takes into account the attraction of the electron to the nucleus and the average interaction with all the other electrons. So when you do that, you can solve for a better phi 1. Okay? So using the new phi 1 and then the original assumptions you made for phi 3 all the way to phi n, you can solve for a better phi 2. Okay? And then using the new phi 1 and the new phi 2, okay, you can solve for a better, and all the original orbitals for the other electrons, you can solve for a better phi 3. So you continuously improve your wave function. You just keep repeating this. As you keep repeating this, you're going to get, you'll be able to calculate the energies. So this is the formula for the energy. All right? So this E sub I is here. Those are the orbital energies that you can calculate, and you have to introduce this integral right here to get the total energy for your atom. So at each step in your calculation, you'll be able to lower the estimated energy. So you keep repeating this and repeating this. You keep improving your wave functions, your orbital, the functions for your orbitals, until your energy no longer drops. Eventually it will level off. Okay? So you can set a tolerance. Let's say if it doesn't change by more than 0.1%, then you say, okay, I've reached the lowest possible energy I can get. Well, that's the limit that you would expect for. You would expect that from the variation theorem. Remember, the variation theorem puts an upper limit, okay, a lower limit to how low your energy can go. Your energy cannot drop below the true ground state energy, right? So once you reach that point in your calculation, you have what's called self-consistency. So this is known as the self-consistent field approximation. Okay? So you imagine your electron, so you reduce your problem to a single electron problem. Imagine that electron to be moving in a field that is affected by the other electrons. So you do not explicitly take into account the other electrons. You just treat them in an average way.